In this session, we're going to discuss the last part of combinational logic circuits. We will take a look at the other gate types, particularly exclusive OR operator and gates and their applications. And we will take a look at the high impedance outputs as well. Why do we need other gate types? Because of implementation feasibility and low cost. This is the main reason. And you also implement some Boolean functions in an easy way, in a more readable way. And when you draw a circuit or something like this, it gives us a convenient conceptual representation as well. By definition, gates are classified in two groups, the primitive gates and the complex gates. The primitive gates are the gates that we've seen so far and or inverters. The complex gates require more than one primitive operation type for its description. Let's take a look at the primitive gates. First, a buffer, for example, is a gate with the function like this. It's what you have input will be realized at output as well. It's in fact a connection itself. Why do we use it? It's usually done for amplifying electronic signals because they lose some power during the travel. That's why we put some buffers within the path to amplify those signals. That's the idea. And the basic NAND gate, okay, these are your primitive gates as well, and it has the following symbol like this, and an inverter here, and invert symbol. And what we do here is in fact just the AND gate, but there's an inverter in the end. That's it. So it can also be represented by De Morgan in another way. Both are okay. If you take De Morgan complement of that Boolean NAND function, what you get will look like this. And this type of gate is called invert OR gate. They both do the same thing. And NAND gate is has two symbols, depends on your liking. And an AND gate with one input degenerates to an inverter. I mean, if you have an AND gate like this, and if you, for example, connect a single input to, and what you get here will be the invert of that input. That's it. They're called universal gates because you can implement any Boolean function just by using NAND gates. Okay, you can implement the AND gates, OR gates, or whatever function you need using just the NAND gates. It's possible. We will see it in detail in NAND and NOR mapping sections. And usually it does not have an operation symbol. Okay, it is defined as a Boolean function because it's not associative, and it's hard to deal with non-associative mathematics. That's why it doesn't have an operation symbol of its own. So let's take a look at the other one. It's let's say brother NOR gate. You just put an inverter at the end of an OR gate and it becomes your NOR gate, as you see here. Again, the same thing applies for NOR gate as well. You can take De Morgan's complement and depict it in a different way, like this, invert AND form. It's exactly the same. And again, an OR gate with one input degenerates to an inverter itself. So that's why it's universal gate. The only thing is, for example, missing here is the inverter, and you can also implement the inverters with universal gates as well, NOR gate. And again, it does not have a defined operation symbol as well. So, what about the exclusive OR and exclusive NOR gates? It is also another Boolean function which is used extensively in logic circuits. It can either be implemented directly as an electronic circuit with the gates, like you can implement it as a single gate like this, or you can interconnect other gate types to implement this function manually, let's say. That's the idea. An exclusive NOR function is just the complement of your XOR function, just putting a bubble here in the end. And by our definition, since we use more than one primitive gate here, XOR and XNOR gates are complex gates. We will see. Where do we use them? We mainly use them in adders, subtractors, multipliers, counters, incrementers, decrementers. We will use them extensively in arithmetic circuits part, you will see. And they're widely used in our arithmetic logic units and CPUs as well. So that's why they're popular. They are also used in parity generators or checkers for communication purposes, communication channels as well. That's why they are popular, and they have their own circuitry or gates. The XOR function looks like this. This is your operator, your OR symbol within a circle. So this is your XOR symbol, and what it does is in fact catching difference. Okay, this is the Boolean function, corresponding Boolean function for XOR operation. See, if either one of the outputs are different, like if it is 1 0 or 0 1, this XOR operation will give you 1. If they're same, it's not easy to, you cannot get 1 here. The result will always be 0. And XNOR function is exactly the inverse of that operation, so it is different now. If they are same, the output will be 1. That's why it is called the equivalence function. This one catches the equivalence between the inputs, and this one catches, let's say, the difference. Okay, the difference between the inputs. That's it. Normally they don't have more than 2 inputs. But if you want to have a system with 3 or more input XOR and XNOR gates, you cascade them, and they are called odd and even functions, depending on counting the number of ones in their index values. So here you see the truth tables of them. Okay, this is your difference function, and this is your equivalence function. It is also, XNOR function is also denoted by the operator, this one, equivalence, by its name. The XOR function can be extended to 3 or more variables, then it becomes an odd function, mod 2 sum. It is also another name for this. For example, if you expand this function here, it looks like this. But when you try to implement it, you will need to have 2-level XOR gates, for example, for implementing such a function. That's the idea. But what it looks like this, all the combinations here. Okay, so the XOR identities are, these are its properties. If you XOR an input with 0, you will get itself. If you XOR an input with 1, you will get inverse of it. If you XOR an input with itself, you will eventually get 0. And if you XOR an input with its inverse, you will eventually get 1. So it is commutative and associative as well. So here is your XOR symbol in the circuit, and here is your XNOR symbol in the circuit. This is shape symbols exist for only 2 inputs. If you want to have 3 input, as I told you, you need to cascade them. The simple sum of products implementation uses the following structure. If you want to build this XOR gate with your simple gates, you will have something like this. You remember X, not Y, C. And this is the implementation of this one. And of course, an AND-only implementation is possible. We will not go in detail of this one. We will discuss this in NAND mapping, but it looks like this. You see, there are only single type of NAND gate here since it's a universal gate. And what are the odd and even functions? The odd and even functions on a K-map form checkerboard patterns. That's the idea about it. And the ones of an odd function correspond to min terms having an index with odd number of ones. And if the ones of if your index numbers with even number of ones in it have ones, so it becomes an even function. The implementation of odd and even functions for greater than 4 variables as 2-level circuit is difficult, so we use trees made up of several XOR and XNOR gates for more inputs. Now let's look at an example here for odd function. Design a 3-input odd function, namely this one, with 2-input XOR gates, yes. And when we factor it, you can go this way or this way, it doesn't matter. And the circuit looks like this, okay, as in the implementation. What you have here is the implementation of this odd function. It's an odd function. And you have to keep in mind that in the truth table here, if you, write the truth table here, X, Y, Z, 0, 1, 0, 0, 0, 1, 1, 1, 0. You will exactly see the checkerboard pattern here since it is odd, and in the odd index numbers, like you will have a pattern like this. Okay, that's the idea. This is what we have for in the K-map for this odd function. If you have an even function, it would be vice versa. You will put here then the ones for the even ones you will put. But here, since this is an odd function, we place odds in their correct locations where your index numbers are as well. Now let's design a 4-input this time even function, which looks like this. Okay, with 2-input XOR and XNOR gates. Now we factor them again, and you have an XOR gate here. Since it is even function, we just put a bubble here, and it becomes a NOR gate just at the exit, just at the last part, and the corresponding truth table is, not surprisingly, something like this. Let's draw it. So your corresponding, okay, since it is even function, you just look at the number of ones in your let's say index number here. You count them. Since it is 0, it means that this is even, odd, even, odd. You put ones in their even locations, and you will have a checkerboard pattern here all over the K-map. In fact, it's pretty straightforward and easy if you get used to it, not a big deal. Now, how do we build parity generators and checkers in this manner? If we want to have an even parity circuit, we need to have an odd function generator for this purpose. If we want to check, for example, even parity of even parity data, we need to have an odd function checker as well. Now let's take a look at what does it mean. Suppose that this is your data, original data, and you want to add a single parity bit to it, which is odd parity. then you will need to I'm sorry, you need to have even parity code words, right? So you need to have an odd function here. Look, if you have 0, 0, 1, this will give you 1. It will be even parity, right? That's the idea. So I put an odd function here to generate even parity. That's what I do. And on the receiving end, this is how I transmit my signal in 4 bits. Okay. Now, these 4 bits are received by our destination, including the parity bit, and it will give an error signal 1 if there is an error present. It means that if it is an odd function, again, the number of ones here is 1, is odd, then it will give us an error. So I put another odd function here as well to check this. That's it. That's all about the parity generators. Okay, now let's take a look at the high impedance outputs. It's a bit different than what we've seen so far. Logic gates introduced thus so far have 1 and 0 as output values, and we cannot have their outputs connected together, and they transmit signals on connections in only one direction, right? Okay, this is what we know so far. But three-state logic changes this. It adds a third logic value, which is called high impedance. And it gives us 3 states instead of 2, 0, 1, and high impedance on the outputs. And the presence of high impedance state makes a gate output behavior different. Like now you can have the outputs connected together in the circuit, and you can transmit signals in different directions as well. So what is a high impedance value? The high impedance value behaves as an open circuit. This means that looking back into circuit, the output appears to be disconnected, like another direction looking. It is as if a switch between the internal circuitry and the output has been opened. This is how it looks. And high impedance may appear on the output for any gate, but we restrict the gates to just to understand how it works. With the simplest one is a 3-state buffer. Your buffer is normally like this, but here in this case your buffer will look like this with an enable here, and it has a data input and one control input here as well. It looks like this exactly, as you see, and its truth table looks like this. So when it is not enabled, the input, you don't care about what the input is because it's not enabled. The output will be always open circuit, high impedance. And if it is enabled, great. Now it works like your original buffer, like here in this part. If you give 0, you will get 0. If you give 1, you will get 1 in the output. That's it. That's it. You can also invert this enabling signal due to your liking or design. So what you have to keep in mind is this is your data input and this is your control input. Now, when we connect 2 3-state buffers to a wire out, if we connect them together, what happens? There will be combinations, of course. Now, this is your first buffer, and this is your second buffer, let's say. So this is not enabled, and the output will rely on this 3-state buffers data. And when this one is disabled, this part is disabled, the output will rely on this buffers, B0 buffers data. That's it. If you disable both of them, what you will see will be open circuit in the connection as well. So let's try to answer these questions. At least one buffer output must be high impedance. Why? Because if we connect, for example, 0 and 1 together to each other, like the output is coming with 0 and 1. Okay, you will burn the circuit, right? That's why. And how many valid buffer output combinations exist here? As we look at the resolution table here, or the truth table maybe, so what you see here is 5 different combinations exist. And what is the rule for n 3-state buffer connected to Y route? So, if you have, for example, n buffers connected together here, suppose that you have lots of them connected to a single output here, like they will be connected here, it means that at least n minus 1 of them should be high impedance, right? So otherwise you can burn the circuit. And how many valid buffer output combinations exist here? You can directly see here it is 2n plus 1, right? If you have, for example, 10 buffers connected to a Y route, it means that you will have 21 different input combination, valid output combinations here. And the last one is, this plus 1 is this one, the high impedance one, that's why. Okay, let's take a look at a 3-state logic circuit and how we can use it in an interesting or beneficial way. So you have here 2 buffers, and this one is disabled here, so 0, 1, buffer 0, and the other one is enabled, and you see its reflection in the output, that's it. And in the second set of rows, you see that this one is buffer 0 is enabled this time, and you see its effect on the output. I'm sorry, not this one. You see its effect on the output here, see? And the other one is disabled here. That's the idea. If both of them are disabled, right here, you see both of them are disabled, you see open circuit in the output. See this one, this is how it works. If you make a connection like this, you can be sure that you can feel safe that, of course, we omit the circuit delays here, gate delays here, but ideally as a model, these two can never be active at the same time. This is what guarantees us that. If this one is enabled, for example, if you send one signal here, it means that this one will be selected, this one will be not. And if you send 0 signal here, it means that this one will be selected and this one will be not. So there won't be the problem of shortcutting the outputs here or burning the circuit. Ideally, of course. And are there more complex gates? Yes. And they are usually sum of products and product of some structures with or without an output inverter. And the names are derived using their first letters here, A, O, and I for the inverter, and the number of inputs on the first level of gates and second level of gates are given here. So here we look at an example here with like 2 A, O, 2 to 1, for example. This one corresponds to a 2-input and 2-input and extra OR input driving an OR gate. This is what it looks. Now let's take a look at some examples of them together so that I hope you will understand it better. Okay, let's start with the example in the text, A0221. It looks like this. It means that my AND level will have 2 input, okay, AND gates, and 1 input AND gate. No, that's not possible. And they will be connected to an OR gate in the end. So that's how we use it. So you draw it like this. You have an AND gate, and you have an OR gate here, and you make the connections, 2 input, and this is your 𝐸𝐸221 gate. Okay, what else can we do? Let's do another one, AOI, for example, this time 2-1. So this port is related with the first level, okay, and this port is related with the, let me just use the same color. This one is related with the first level, this one is for the second level. Finally, we have an inverter here, it's also located here. So you have them, an AND gate, an OR gate here, and an inverter here in the end. You see, that's it. So you have two input and one extra input connected to an OR gate, and it looks like this. Okay, let's do more. OAI21. It looks like this. Maybe you're already getting familiar. I think it's easy, right? Since it has an inverter here. Good. And another one, OAI32. What do we mean by this? We have two OR gates connected to an I inverter. Have 3, 2, connected to. This is how it goes, right? This one is this one. This one is this one. And your AND gate is here. And your inverter is right here. So that's it. And finally, let's do the last one, AOI33, and it will look like this. Okay, and see these ones, okay, and they will be connected to an OR gate, and there will be an inverter here. So it will look like this. Okay, the idea is if you want to implement this with the primitive gates, I checked this somewhere, but it's in my notes, but I forgot where I took it. Most probably from Wikipedia or something like this. If you if you want to implement this, it will cost you like 8 transistors, and here you will have 8 transistors as well for this 3 input AND circuit, and here you need 4 transistors for this, and for all of them 4 transistors, and it will result in 20, right? 20 transistors for implementation or your total cost. But if you have it as a pack like this, complex gate produced for working just like this, it will look like this: 6-pin input and 1-pin output. It is like in a pack. If you implement it like this, it will cost in only 12 transistors here. Not only your total cost will be lower, but also the speed of your circuit is faster if you implement this as a box solution to just implement what you're seeking here, what you want to do here, instead of building them with the primitive gates. That's why sometimes using complex gates or having them can be beneficial. Just imagine you will have this structure, let's say 10,000 times, so it would be much more convenient if you implement them as complex gate, both in cost and speed as well. So that's it. That's all about the today's session, or this session. So we discussed the additional gates and circuits, and we will continue with combination logic design procedure in the next sessions. Thank you for listening.